Welcome everybody. We're going to cover a lot again today. We're going to work some more with polynomials, and what I want to start with now is how to break them up into pieces. So here we have a cubic polynomial, and what I want to know is what is this in factored form? We factored quadratics earlier. How do we factor bigger polynomials? Step number one is always look, is there something common to all the terms you can factor out first? And if you look, you notice all three of these terms have an x. So factor out the x first. So pull the x out, divide it out to the left like this. And then write what is left in each term. So this would be x squared minus 2x minus 15. So that's backwards distributive property. If we multiplied all three of these terms by x, we would be back at where we began. Now I have a quadratic, and you know how to factor quadratics. So look at these. Are there factors of negative 15 that add up to negative 2? And there are. Negative 5 and positive 3. So this factors to be x minus 5, x plus 3. Don't forget the x out in the front. This is this cubic in factored form, all broken up into its little factors. I really want you to pause the video and take the time to try to do this. Here's another one on the board, x cubed minus x squared minus 12x. Go ahead and pause, and what would this be in factored form? And come back and I'll walk you through it. Okay, you should have seen that x was common to all three and factored out that first. Then look for factors of negative 12 that add up to negative 1. That would be negative 4 and positive 3. So that's x minus 4, x plus 3, and the x out in front, and that should have been your answer. How did you do? I hope you did well. Here is a function. Notice I have the y equals. So now here's a polynomial function. It's already factored for us. And now the question is, what are the zeros? So if this is 0, what would my x's be? What are the zeros? A difference between factors and zeros. So look at these terms one at a time, or these binomials. What would make this binomial 0? It would be negative 2, because negative 2 plus 2 is 0. So your first 0 is negative 2. This 0 would be positive 1, because 1 minus 1 would be 0. And this 0 would be positive 3, because 3 minus 3 would be 0. So our three zeros of this polynomial are negative 2, 1, and 3. And now the next step is graph it. How would you graph it? So let me show you that. Okay, step number one is to take those zeros that we found and plot those on the x-axis. Those are their x-intercepts, are the zeros. So we'll start by plotting those 3 points. The 3 zeros were negative 2, positive 1, and positive 3. Now we don't know what this graph is doing in between or at either end of those points. So at this point, we'll build a table. And when we select points for our table, when we select our domain or our x's, pick x's that matter. Pick ones that are in between here so we can see what the graph's doing, and at either end. So since this is negative 2, what is this graph doing at negative 3? So I'll pick that. What is this graph doing when x is negative 1 and 0? So I might do those two. And what is this graph doing at 2? Because that's between these two zeros. And finally, on the outside edge, what is this graph doing when x is 4? Now, how do you plug them in? You plug them in into each binomial expression. So negative 3 plus 2 is negative 1. Negative 3 minus 1 is negative 4. And negative 3 minus 3 is negative 6. When I multiply those 3 together, I get negative 24. So when x is negative 3, y is negative 24. That's way down here off my graph. Okay, let's do the same process when x is negative 1. I plugged -1 in each of these binomial expressions, and I got this one came out +1, -2, -4. When I multiply those together, I get +8. So when x is -1, y is 8. When x is 0, I come out with 2, -1, and -3. Are you seeing how I get those numbers? So when I multiply those, I get +6. So when x is 0, y is 6. Okay, when I made x2, this one was 4, this one was 1, 2 minus 1 is 1, and 2 minus 3 is -1, and when I multiply that, I get -4. So when x is 2, y is -4, and now I'm going to do 4 next. And when I made x4, I got 18. So the last step is to plot those points. 3, -24 is off my graph, but -1, 8 is up here, and 0, 6 is up here. So let me plot those. Okay, now remember I connect the dots in order from left to right. This one is way down here. It's going to come up here, turn, go through there, turn, and go up. And there is my graph. It could go a little bit lower, a little bit higher, not exactly sure, but this is close enough for me, that's for sure. Could you put this in your graphing calculator? Yes, you could. You could enter in this factored form and then hit graph, and you would be able to see this on your graphing calculator as well. I can help you with that during class. If you have one, bring it. Here's another one where it asks what are the zeros and then graph it. When you see this x by itself, that zero or that factor would be 0, because that as 0 would make this whole equation 0. So this one is 3 and this one's -5. So in order, they would be -5, 0, and +3. So what you would do is graph those on the x-axis, those 3 points, find the points in the middle, and then connect the dots in order from left to right. I'm not going to walk through that. That would be a good exercise for you to do though. Notice these were factors, and from the factors, I got my zeros. Doesn't it seem logical that if I was given my zeros, I could figure out what the factors are? That's what we're going to do next. So now you're given a problem, and it says, what is a cubic polynomial with these zeros? It has a 0 of -2, 2, and 3. So from the zeros, what are the factors? That's what you do. And it is a cubic, which means there's 3, it's x cubed, so there should be 3 factors, 3 x's you're going to end up with. And sure enough, you have 3 zeros. This one, just pick the sign opposite. If this is -2, then the factor would be x plus 2. Do you see how that's a 0 for this factor? If this 0 is +2, then its factor is going to be the negative, it's going to be x minus 2. And if this 0, is +3, then its factor will be x minus 3. It's going to be the opposite sign. Now double check yourself. Is -2 this one 0? Yes, it is. Is 2 this one 0? And 3, yes, it works. So this is actually the cubic in factored form. You, however, are not going to leave it in factored form. What they want is this whole polynomial multiplied out. How do you do that? So first, take 2 at a time. Take these 2, since these are a matching pair, and FOIL them. These 2 FOIL out to be x squared minus 4. Now I will take that and multiply it by x minus 3, and I will FOIL that. I'll walk through this one with you. X cubed times x squared times x is x cubed. This is minus 3x squared minus 4x and positive 12. And there is your cubic polynomial with those zeros. Pretty cool. You just went forwards and backwards. Neat. Here's a similar problem. Notice it's the same 3 zeros except I added an extra 2, and now I'm asking for a quartic. So that means there's 4 this time. So I have 2 -2s. That means I'm going to have 2 factors x plus 2. X plus 2 times x plus 2, x minus 2, x minus 3. Now when I multiply, you can multiply in any order you want. I really want to make this as simple as possible. So what I notice is these two are a difference of 2 squared, so I'm going to multiply those two first. Because since it's a difference of 2 squares, those middle terms will cancel out. This will become x squared minus 4, so I know enough to do that. That helps me. So I've multiplied those two. I got x squared minus 4. Now I'm going to multiply those by x plus 2, and because both of them just have 2 terms, they're both binomials, I can FOIL. I still have one more term to multiply by this. That's x minus 3. How am I going to do that? What I'm going to recommend is that you do this the way that you did back in elementary school when you had to multiply long numbers. Put the bigger number on top, the smaller one down here, and multiply just like you did. Remember when first you would multiply all of these numbers by the far right? Let's do that. So first we will multiply all of these by negative 3. Negative 3 times negative 8 is positive 24. Negative 3 times negative 4x, positive 12x. Negative 3 times 2x squared, negative 6x squared. And negative 3 times x cubed, negative 3x cubed. Now multiply all of these by x. Write your answers below it, combining, putting columns of like terms. So first, x times negative 8 would be negative 8x. I'm going to write that below my 12x. Positive, then times negative 4x would be negative 4x squared. Times 2x squared would be 2x cubed. And then times x cubed would be x, positive x to the 4th. Now I'll do just like you did in elementary, you just add columns straight down. So we have 24 here at the end. 12x minus 8x is positive 4x. This is negative 10x squared. This becomes negative 1x cubed and x to the 4th, and there you have the entire quartic all multiplied out. So all those wonderful multiplication skills that you learned, you still use them. They don't go away. That's the simplest way to do this. Just be careful. Like terms, watch your signs. In your text it says to graph both of these and to see how they're similar and how they are different. And it's a wonderful, I could try to draw it, but I'm not going to. I'm going to explain a little bit about it. But they used a graphing calculator. Notice the x-intercepts were the same, except because this was a double 0, it behaved at that point on the graph differently. Instead of going straight through the x-axis like it did in the cubic, it went to that negative 2 and it turned. It became a turning point. And that's what I want to talk to you about now. In that quartic that we just did, negative 2 was a 0 2 times. So it had a multiplicity of 2. In other words, it's just multiplied by 2. This was a 0 once, so it has a multiplicity of 1. This was a 0 once, so it has a multiplicity of 1. But this has a multiplicity of 2. And why that's significant is those are all points where the graph crosses the x-axis. But if it has a multiplicity of 2, that means it touches that number and then turns and goes back the other way, just like a quadratic at a vertex would behave. That's the way it behaves there. If it only goes through just that that number is a 0 once, a multiplicity of 1, then it just goes straight through like a line at that number on the x-axis. What if it has a multiplicity of 3? So it actually 3. Then it would behave like an x cubed. X cubed kind of does this type of thing. Kind of like that. That's what it would do at that 0 if it had a multiplicity of 3. So you're going to be asked about multiplicities. You would say this is a 0, negative 2 is a 0 with a multiplicity of 2. So, and these both are zeros with a multiplicity of 1. Please understand how that behaves. If it's a multiplicity of 2, it behaves like a quadratic and it turns. If it's 1, it behaves like a line. It just goes straight through it. Okay, so you can get a question like this. What are the zeros of this polynomial function? What are the multiplicities of those zeros, and how does the graph behave at them? So first we're going to factor it like we did before. I'm going to look for something common to all three, and then they all have an x squared. So I'm going to factor out the x squared. Now I'm going to look at what's left and factor that. There are factors of -8 that add up to -2. It's x minus 4, x plus 2. Those are those factors. So now we can answer the question, if these are the factors, what are the zeros? This one is just 0 because it's by itself. However, it's squared. So our first 0 is 0. It has a multiplicity of 2. I should show you the reason why that's 0 is because this is actually this factor. X minus 0 squared, or yeah, x minus 0 squared. Well, you don't need to write the minus 0. That's why it's just x squared. And that's why it's 0 is 0. This 0 is positive 4. This 0 is -2. Okay, so I've taken the time to write out my zeros and their multiplicity. 0 has a multiplicity of 2. 4 and -2 have a multiplicity of 1. What is my graph behavior? At 0, my graph is a turning point. So it's a turning point at 0, and it behaves like a line at 4 and -2. And that's how you would answer that question. Before I go over the next thing, because there's a lot to this lesson, I want to show you my lesson check for today. The lesson check is, what's the quadratic of what's the polynomial function of a quadratic with zeros at 3 and -3? So if these are my zeros, what quadratic has those zeros? All right, so that's your lesson check. Bring that in to me and I'll know you watched this video, or at least most of it. Earlier we graphed a cubic that had some big curves in it. I just drew another one just kind of freehand to show you what we're going to talk about next. And that is maximums and minimums. When we dealt with quadratics, we realized the vertex was either going to behave like a maximum if the quadratic opened down, or like a minimum if the quadratic opened up. But in these polynomials, we have several, or can have several different turning points. We still want to talk about maximum and minimums, but now they're not overall maximum and minimums, they're relative maximum and minimums. So in other words, they're just relative to its neighboring area. So this behaves similar to a vertex. This is a relative minimum. What would that point be? This one would be a relative maximum. Your textbook asks you to do that and basically just says, use a graphing calculator to determine what it is. If you graph by hand, you have to kind of estimate it as best you can, where a graphing calculator can get really close. So that's what this is about. So this is the example problem in your text. It says, what are the relative maximum and minimums? So you would actually, this is the y, you'd put in under your y equals button on the graphing calculator, x cubed plus 3x squared minus 24x. Then you'd hit the graphing window, or you'd look down at the table and try to find the relative maximum and the relative minimum points as best you can. If you don't have a graphing calculator, that's going to be really tough. You may not be able to do that. You may not be able to do those online either. Look through the example and it may just say, use a graphing calculator, use a graphing calculator. There are, when you're working on the computer, there are online graphing calculators. Desmos is one. That might be able to do the work for you, which is pretty nice. You can enter in the information, have it graph, and then analyze the graph right on the computer without having to spend over $100, because this is free, without having to spend over $100 on a graphing calculator. So try those different options so that you can do the best that you can. Okay, the next problem is a real challenge, and you will see this type of problem on at least a quiz, if not a test. So I'm really glad you stuck through to the end of this video so that I could walk you through it. Let's say the problem is that you want to maximize the volume of a box. You want it to hold as much as possible, but the sum of all the dimensions has to stay 6 inches. So when I add the length plus the width plus the height, they're going to add up to be 6 inches. What should those dimensions be so that I have the maximum amount of volume in my box? And you're going to learn how to find that out. So first, they tell you the length, they want the length to be 1.5 times the height. You need some information to do this. So that helps a little bit. Now what we need to do is we need to come up with terms to represent the length, width, and height, but we really want them to be just with one variable. If we're dealing with L and W and H, it's just too much. So we want this to deal with just one variable. We are going to use this and this information. Since the length is 1.5 times the height, let's make the height be X. So if we designate our height as X, and we know the length needs to be 1.5 times the height, then let's make L 1.5x. Now the challenge is, what do we make the width? And how in the world are we going to keep that in X? And we are going to use this as our means of doing that. Because if I add L plus W plus H, they all have to add up to be 6. So if I want to find the width, I have to subtract the length, and I have to subtract the height from 6, right? Take 6, take away the length, take away the height, you're left with the width. So my width is 6 minus 1.5, x, and minus 1.5x. Let's simplify that. This expression would represent our width. Okay, now we are wanting to maximize the volume. How do you find the volume of a box? It's length times width times height. X times 1.5x times 6 minus 2.5x. You can do it. X times 1.5x is 1.5x squared. Distribute that through this expression for our width. And we've done it. It's not in standard form, so let's put it in standard form. There's our polynomial, which represents the volume. So if you have that graphing calculator, huzzah, go ahead and plug that in, or enter that in under y equals, and hit graph and see what your relative maximum is. If you don't, then graph it by hand. These two are zeros, so two of my zeros are 0 twice. So I have 0 and 0. To find this one, I set this equal to 0, negative 3.75 x plus 9 equals 0, which means negative 3.75 x equals negative 9, so x is negative 9 over negative 3.75, and use your calculator to see about where that is on the x-axis. So my other 0 is at about positive 2.4. So I would plot those, look at the points in between. This was a negative cubic, right? So it's going like this. So probably up in here is where my relative maximum would be, in between these two. So graph those points in between and estimate best you can, or use a graphing calculator by all means. It would be so much easier. The main part of this is setting up your equation. That's the main part. Okay, I'm going to cut this off now because there's a lot to do in this section, just like there was in the previous one. A lot to cover in one section. So work through this best you can. Don't forget to look for those online resources for graphing calculators if you don't have one of your own. And I will be sure and help you in class as much as I can. So I'll see you guys later. Bye for now.